Now it's time to present our next presenter. As I said, he's coming from Mexico and he is Luis Héctor Chávez. He's lead platform engineer at Replit, pushing the boundary of what online coding environments can be. So please welcome on stage with a huge applause how Replit manages hundreds of thousands of containers. Luis Héctor Chávez.
Here. Hi. Good afternoon, everybody. My name is Luis Héctor Chávez. I am the lead platform engineer at Replit. And I'm going to talk about how Replit manages hundreds of thousands of containers of user code containers. So, first of all, this talk is going to be divided in 3 sections. What is Replit? Because I'm pretty sure that, actually, show of hands, who has heard of Replit before? Oh, wow, surprising, cool, thank you very much. The next section is going to be the architecture of the container serving infrastructure at Replit throughout the years. And the third is, okay, so we're going to be giving out free compute. What could go wrong? That's going to be a fun section. So first, for the people that didn't know what Replit is, I'm going to give a very, very short introduction, mostly for context-setting purposes. I'm going to start with the mission. The mission of Replit is to bring the next billion software creators online. And in order to do that, we build powerful, simple tools and platforms for learners, educators, and developers. What do these tools look like? This is probably going to be the most recognizable screenshot of Replit. We call this the workspace. And the workspace is a full-fledged IDE online. It comes with whatever you expect in an IDE. File picture, the editor, of course, a preview if you're building an online application. It also can have a debugger, package manager. You can also see like a shell over there, and you can run your applications all in this in the workspace. Now, on the workspace where you're editing is a project, but we affectionately call the projects REPLs, based on the fact of a historical fact. When the company started, it was only an online interpreter. Most interpreters are based on a scheme of working called the read, eval, print loop. Read, eval, print loop, REPL. So that is the reason why we call this REPLs. And REPLs have 2 parts. A static part, which consists of all the files that are found in your project, in your REPL, and a dynamic part. The dynamic part is running in a Linux container. So that is why I'm going to be talking about Linux containers. One important thing about the workspace is that, as opposed to many other online IDEs, Replit is fully collaborative, meaning multiple people can be working at the same time on the same REPL. So multiple people can be like editing the code, but also other features of the workspace enable collaboration. For instance, you can also have whiteboarding tools so that you can diagram and draw some nice stuff. You can also add annotations to the code, so you can do like code reviews. We also have like collaborative debuggers, so multiple people can be like debugging the stuff at the same time, so on and so forth. But that's not all that we provide. We are cognizant that the next billion software creators are most likely not going to be like top experts. They're not going to necessarily know beforehand how to write software. So we also have a community. This community is built so that all the people that are trying to get into programming don't need to go there alone. So they support each other. And we also have standalone tutorials and self-guided guides so that folks can learn how to program by themselves. And finally, we also have a product for larger teams. So think about a company that is interviewing people, or a school. And actually, schools are the #1 users of this offering, mostly because we provide additional privacy features. We also provide different ways of collaborating. And for schools specifically, we also have a little feature to allow you to create coursework and also automatically grade your assignments, which is super nice. In the past few years, where most education went online, but still today, it's being used at a lot of schools because of the additional collaboration features that are still used for in-person learning. And we do a bunch more stuff. As I mentioned, we also let you host your projects online so you can build online applications. We have 80,000 software packages that are pre-installed in every REPL, courtesy of the Nix package manager and Nix operating system. We have a game editor to make creating games fun and easy called Kaboom.js, and a lot more things. OK, end of that. Now into the good stuff. At its core, we chose the REPL as the user-visible primitive. This means that we built most of our features based on Linux containers. And most of the abstractions that we present to people are behind the covers, just a Linux container with some stuff. Also worth mentioning is the concept of REPL space. REPL space is a word that we made up, but it has its origins as an analogy to an operating system concept called kernel space and user space. Kernel space is the segment of memory that a machine has that is only accessible by the kernel. And it's also the place in the machine where all the kernel features live. User space, by contrast, is where all the user applications or applications that users can start and interact with are running, and the way the kernel manages isolation between them. So by extension, REPL space is everything that you can run on a REPL. Of course, REPL space is a subset of the user space because it's still running on a Linux machine. And we try to make REPL space approach the same capabilities as user space as time goes on, meaning we do have some limitations compared to user space, but our plan is to make those limitations go away eventually. Right, part 2. Now that we know what Replit is, let's take a short tour over the architecture of Replit's infrastructure to our time. This is the very first version of Replit, just an online editor and an interpreter. This was done in 2009, and it was implemented in Asm.js. It used mscripten to compile the interpreters into JavaScript, and it was very hard, just because Asm.js is a very limited runtime environment. You can only do effectively number crunching. Like you can process numbers, and that's it. Everything else is just smoke and mirrors. This is a phrase I stole from yesterday's presentation from WebAssembly. And since it had a lot of limitations, well, there were only a few dozen programming languages supported. If we were to draw an architecture diagram, it would look pretty simple, just like this. You have a server where the static assets are stored, and you have a client where everything is run. And when I say everything, it's everything. The rendering of the components that are run in the browser, and also the user code is being run in the browser. This has a very important property. If everything is run in the client, that means that we effectively have infinite scalability. Hooray! However many users are going to run the software, we can handle it because we're not effectively running in the compute. Mission accomplished. Well, not quite. This infinite scalability came at a very steep cost. The first one, as I mentioned, Asm.js environments have significant feature compatibility problems just because they're a very constrained environment. So it is difficult to port any runtime like super simply with 100% compatibility. And the second is that there's a non-trivial performance overhead. Most of us have the privilege of having very powerful machines to run our code on, but not everybody does. Some people only have access to a mobile device to use the internet. So for those folks, on top of having to run all the code on a JavaScript virtual machine, or JavaScript interpreter, or whatever, they also have to deal with the fact that their devices are slow. So this experience wasn't great. What did we learn during this phase? First one, we proved the concept. We realized that people wanted to have an online IDE. And even with limitations, it was still useful. There were some people that were using this opportunity because they had no alternatives. Like I mentioned, some people only have a phone, and on a phone you cannot effectively program unless you resort to systems like this. And finally, maintenance can be a deal breaker. Given that building stuff for Asm.js is super complicated, it took several engineer days just to update one existing language. And I'm not even talking about supporting a new programming language. That was a weeks or months-long endeavor. So, fast forward a little bit, 2016. Containers are now mainstream, thanks to Docker and Kubernetes. So the team said, what happens if we try to, instead of running the code in the browser, run the code in the cloud? Fortunately, by this point in time, running containers on the cloud was super cheap. So why not try it? And they did. This is a screenshot of the new version of the platform. Same thing, you have an editor, you have a shell, but instead of just having a REPL, this interpreter is actually backed by a machine in the cloud, a full Linux container. Now, one of the good things about Linux containers is that they're reproducible, so that if you install some software in a Linux container image, it's there forever, and it runs no matter where you are, in theory, unless the kernel changes or something. But for Replit, it meant that since most language maintainers create Linux container images on their own, we just had to import those things and run them in the cloud. Problem solved. So now that we have a server component, the architecture diagram is going to be a lot more complicated. First of all, this middle section is the path that the workspace is going to use to connect to interact with the container. The workspace is just like a shell that users are seeing. All the computation is done by a Linux container on the cloud. So here is where the Linux containers on the cloud are running. But we need a way to prove that a particular client has access to that particular container, because otherwise folks would just like, hey, give me access to your container. I want to see your files, and I don't have any permissions to view it. Like, sure, go ahead. We wanted to prevent that. So in order to do that, the client contacts the web server. The web server gives it back a token. This token is just a cryptographically signed message that has the privileges and permissions that the user has to run a container. It has the CPU quota, the disk quota, memory quota, all those things. And also the ID of the REPL that it's trying to contact. Once the client has the token, it creates a WebSocket connection. We chose WebSockets because it provides bidirectional communication between the workspace, the interface, and the actual Linux container. And this WebSocket has protocol buffer encoded messages so that it can send commands like, hey, please run this particular shell, or hey, please start a debugger, or please give me the list of files, so on and so forth. So when a client creates a WebSocket, it hits a load balancer. This load balancer contacts one of several thousand machines, VMs on the cloud. Each one of those VMs is running 100-ish containers. So this is how we achieve horizontal scalability at this stage. In 2018, we added the hosting feature, which means that if a program in a REPL starts a HTTP server, we route it to the internet with a .repl.co domain. And in order to do that, the clients contact a different server, the .repl.co load balancer. This forwards the request to another set of virtual machines. And these virtual machines look up the port and IP address of every single REPL that has open that has an HTTP port open. This lookup is done through a database. This particular interaction between the hosting experience and the containers add one quirk. The containers may outlive the WebSocket connection, and this is just because otherwise, if you're not actively looking at your container, you wouldn't be able to interact with the server. So in the end, the container manager service, which we effectively call Conman because we're super creative, is effectively a cooperative, optimistic distributed system with distributed logging, which means that the first time a WebSocket connection lands on a container manager virtual machine, it checks if any other of the container manager services VMs that are running already has a claim to that particular REPL, that is already running a container for that REPL. If it hasn't, hooray, it creates a container and registers it in the database. If some other machine has created a container, then it transparently proxies the original request to the virtual machine that is running the container. That is why we have a dense end-to-end square graph on the left-hand side. And now each one of these container manager machines has like 100 containers. And all these containers have one process called PID1. We call it PID1 because, well, its PID is 1, similar to how systemd and initv work in traditional Linux. This PID1 is the termination of the WebSockets, meaning that the workspace is interacting directly with this particular program, and is the one that decodes all the messages and handles the execution of all the programs. Lessons learned. Now that we have a way of running code online on containers, we created this abstraction, the REPL. And now that we have this abstraction, we can build a lot more things on top of it. So we can create, if you want to fork or remix a REPL, you can just like clone the file system and put it on another REPL. And now you have 2 copies of the same thing. Another thing that we learned is that even though we lost the property of having infinite scalability, we still wanted to have horizontal scalability. So we didn't want to mess with like having to create virtual machines one by one and manage the number of virtual machines. Instead, we delegate this task to the cloud provider, in our case, Google Cloud, the cloud platform. Another thing that we learned is it is better to ship fast than have a perfect design. This particular design lasted 4 years, and it was made not to provide the best possible properties, but rather to be flexible, to be customizable, to be able to experiment a lot. And in retrospect, this design lasted 4 years. 4 years in internet time is a lot, which means that it had some good things going on for it, but it had some flaws, of course. One of the most critical things that this particular design had is that it's effectively a single point of failure. Since we have a single pool of containers, if anything goes wrong in any part of that process, the whole site is down. And that's kind of sad. So after a lot of incidents, we decided to create a brand new version of this architecture. Enter failure domains. What is a failure domain? A failure domain is a subset of like a system that if it has a problem, everything fails. Conversely, if you have 2 different failure domains and one falls down, then the other ones can continue working independently. So we decided to partition our user base into multiple tiers. Our free tier that we call the global tier, and the paying tier, which we call the hackers, just because that's how we market our paid offering. In order to create the failure domains, we needed to have independent infrastructure for all of the failure domains. So we did just that. If you remember the previous slide where we had this particular section of the diagram, we just made several copies of it, one for every failure domain. But now, the problem is that any individual REPL must belong to exactly or at most one failure domain, which means that we now need to have a lookup service. That lookup service is the thing that is on the top-hand side. For our internal infrastructure, having a simple RPC service with like REST or something like that is sufficient because you can just like query this service over HTTP or whatever. But what happens with the hosting offering? People don't necessarily want to change their URL address to like global.repl.co because they're on a different failure domain. So before we made this change, when people wanted to hit this load balancer, they used the DNS infrastructure, the internet's DNS infrastructure to get the IP address of that load balancer. So we said, if this is already using DNS, what happens if we roll around DNS infrastructure? Said one engineer in one Slack message. And we actually just did that. We rolled our DNS infrastructure despite warnings that was very complicated. But it worked. Now, whenever people request a hosting REPL, they just go to the DNS service. It tells you the IP address of the individual load balancer of that failure domain, and you're good. Everything works. So what were the lessons learned in this stage? Now we had one more abstraction, the failure domain. And we could use this failure domain, this new abstraction, to build more things. For once, now that we had different infrastructure for the paid and free tiers, we could get a better quality of service for the paid tier, meaning we could give a slightly lower density of containers per VM which meant that the Repls of paying customers will now have to compete with fewer other containers, which made them faster, or perceptibly faster. Another thing that we gained at this stage was the fact that we could now have a staging environment. Yes, this was kind of late to have a staging environment up to this point, but we were happy that we actually had it. And finally, it enabled us to experiment with some other stuff. Given that we needed to recreate the deployment infrastructure just to pull this off, we decided, what happens if we create a footprint in India for our customers in India? Well, turned out that that had terrible implications. Reason. The load balancer by default tries to place your request into a server that is geographically close to the user. That is one of the best features of GCP's load balancers. What happened was that we're not a common use case for load balancers, because load balancers assume that every single request has more or less the same cost. Whereas in our case, they are super long-lived, and they can have massively different costs associated. If somebody's just editing a small file, super cheap. But if somebody's like running, I don't know, SciPy or TensorFlow, or things like that, those containers are really expensive, and we have no way of knowing ahead of time. So, picture this. User in India creates a container. It's landed in India. A couple of hours later, the load in the India GCP region is increased, so the load balancer says, I need to place that request over where there's capacity. Let me place it in the US. Now, I had mentioned before that if you land on a VM that wasn't hosting your container, it transparently proxied back to the VM that had your container. So, user in India creates a container in India and then connects to a VM in the US. So now they're ping-ponging across the globe just to create a round trip. So instead of making things faster, we actually made things slower. Whoops. So in order to overcome that problem, version 1.2. Now we have a control and data plane separation. So what is a control plane and a data plane? The control plane is the set of requests that ask the system to mutate its state. Meaning, we now had an explicit way of telling the container infrastructure, please create a container, and please create it in this particular region of the world. And the data plane is where you move bits around. So for Replit, that is both the WebSocket connection and also the HTTP connections. So now, instead of having to rely on the load balancer to decide in which particular VM to place a request, we now have a component that actively places requests on not necessarily individual machines. We still rely on an internal load balancer, but at the very least, we control in which geographical region that particular REPL will live. And that abstraction creates a good property. Now we have data locality. And the data locality is important because we can co-locate the component that is the control plane together with the database. That means that we have lower latency overall, which is great for everybody because now your REPLs feel snappier. Now, unfortunately, we still don't have lessons learned from this particular implementation just because this is still an ongoing process. Just earlier today, a developer flipped the flag to enable it for like 80% of the population. But we still have some projected lessons that we have learned, or at the very least, some. Since we have a new abstraction, the control and data plane separation, we think we can build a lot more features with this new abstraction. So what does the feature hold for us? For one, given that we now have full control over where REPLs are going to live, and we have data locality, that means that we can achieve full separation of compute and storage. Meaning, right now, every single VM has is running the container, and also needs to pull the file system from cold storage, download it into that VM, and then have the container mounted. If we achieve full control, full compute and storage separation, that means that we can have a different service that is running the file systems and the containers, which means that if a container restarts for whatever reason, it can just reconnect to the same storage service. This will lead to even less latency for most operations. Having a separation of compute and storage also means that we can deprivilege the machines that are running untrusted code, which is great for security. And that also allows us to do some experiments. We're planning to experiment with virtualization instead of just relying on container, just because we know it's more secure that way. Part 3. Now it's time to address the elephant in the room. We are giving away free compute, so what could go wrong? And I'm sure most of you are guessing, like, can people mine Bitcoin on your machines? Well, the answer was yes. What does Replit security model look like? First of all, very openly, Replit is effectively remote code execution as a service. Every time I interview a security engineer, I tell them, you are going to do what you've been trained your whole life to not do, or to prevent actively. We give people a lot of tools. We give them access to a full toolchain, compilers, as I mentioned before, the 80,000 NixOS packages. So the attack surface area is humongous. Users also have full access to Linux containers, so they can just run whatever they want. This means that a allow list-based approach, meaning I only let you run a few things, won't work, just because we want to give people access to more and more tools. Having said that, we do have some restrictions. And we use the usual suspect in Linux containerization. We use namespaces for everything. We don't give root access. We remove all the Linux kernel capabilities. We set the no new privileged bit. We use second BPF to limit the number of syscalls that people can use. And we also uninstall a few kernel modules that have been implicated in a few CVEs, like, I don't know, eBPF JIT, or things like that. We also have a firewall that prevents people from accessing known bad sites. This is especially important for schools, but also because we know that most of our population, a good percentage of our users are minors. And since the allow list-based approach doesn't work, we operate mostly on a deny list-based approach, meaning we try to detect when people are doing bad stuff and prevent that. So we run an automated abuse detection system. How do we do this? We have monitoring. We have lots of monitoring. Since we own the platform and the whole stack, we can see all the processes that are running. We can also monitor resource consumption. We can know, like, a particular REPL is using too much CPU or is issuing too many network calls. We can also inspect the network traffic. We can see all the packets that are flowing through the network interface. And then out of all these things, we extract some signals. And we feed those signals to a very simple model. This model has just two outcomes. To perform an automated takedown, meaning that that REPL is no longer going to be allowed to be run for a short period of time, typically 10 minutes. Or we have a human review a log of takedowns and said, this particular user is doing bad stuff too often. Let us ban them, because they're violating our terms of service. Now, I mentioned that we use this simple model. Why do we want to have a simple model? There are four reasons. Well, four main reasons. The first one, simple models are typically faster. Why do we care about it being fast? Even though this model runs asynchronously, meaning it is not in the data path, it is not blocking user operations, being fast is also a good property because we're running a lot of containers at scale. Every single VM has hundreds of containers, meaning that if this abuse detection model is slow, it's going to slow everything down. At one point, we decided to run a profiler against one of our machines. And we were horrified to find that the feature extraction for one particular input to this model was taking a full core out of a machine. So that's like 12.5% of CPU just running, I don't know, it was regular expressions. We looked at the kind of regular expressions that were being run, and it turned out all the regular expressions we're doing was just substring matching. And substring matching is an operation that modern CPUs can perform like insanely well. So we converted most of the regular expressions to a simple substring match, and boom, we saved one full CPU. Now we have 12% more CPU to give to our users instead of just running this thing. Another benefit of having a simple model is that simple models are typically easier to modify. We don't want to have a few set of people that are the owners of this model. We want anybody in the company to be empowered to make changes to this model. So the simpler the model, the easier it is for everybody to like go hack it, or also see if there are any regressions in the model, meaning you introduced a false positive. And speaking of regressions, simpler models are typically more explainable. Being explainable is a useful property because oftentimes people are going to go to our support team. Hey, my Repl is not working anymore, and it says that I did something bad. What did I do? Then our support team can go and like, oh yes, I see the explanation of the model. Yes, you did something bad. You're violating our terms of services. Goodbye. Or they can say, oh, whoops, this is actually a false positive. Let us tweak the model to make it less aggressive. And speaking of false positives, we also want to have a model that is that has a low false positive rate. Just because every time we say that a particular Repl is bad, we take it down. That is disruptive to our users. So if there's any user that is doing something okay and we take it down, that's an error in the model, and we need to minimize that. All right. So what happens when the detection fails? We still have multiple layers of defense. For starters, we have a fleet-wide surveying. So we aggregate every single signal that we put into the model for the whole fleet, for the whole 500,000 containers that we run. And we look for patterns. Has the CPU of the whole fleet increased in the past few days? Or is this particular host in the network being hit more often? Or is, I don't know, is there a well-known Bitcoin miner that is rampant in our infrastructure? We still don't have an automated way of making decisions based on the survey. So we delegate that to manual surveying. So every now and then somebody needs to go and look at those signals and look and see if they're anomalous or whatever. So this property is good to have multiple layers of defense. We have the automated system, and we have this more manual system to catch all the stragglers. And this works okay for the most part. But we're still trying to improve this the system. Just because like there's one engineer that needs to sit down and actively look at stuff. So going forward, what we want to do is to have more targeted content scanning. Mostly to prevent people from hosting bad stuff, the stuff that we don't want to be associated with Replit on our platform. We also want to create a different set of models for the fleet-wide surveying. And the reason why we want to create different models is that for the fleet-wide survey, it doesn't matter if they're slow. It doesn't matter if they have a high false positive rate. What we want is to have a low false negative rate, meaning we want to catch more stuff there. And we are OK with it being a little bit noisy, just because there's still a human in the loop. There's still a human making the final decisions. And on this stage, it is when the changes to the online model are most effective. And finally, more automation. Even though doing things that don't scale is a good practice for most startups, and we are a smallish startup, there comes a point in which that engineer that needs to sit down and actively inspect the model, it comes at an opportunity cost. That one engineer could be doing something else. Namely, they could be doing more automation. And with more automation, there's a positive feedback loop, because if that engineer is freed from doing this, they can improve the model a little bit more, and then improve it a little bit more, and more, and more, and more, and then the model is more robust. Therefore, the engineer needs to spend less time, or can create better analysis, and so on and so forth. And something important. Why do we want to prevent abusers? Well, for once, abusers are consuming CPU, are consuming resources that we could be giving to other folks. At some point, we realized, like a couple of years ago, that a good 10% of the containers that we were running were just abusers, and they were costing us a ton of money. So having control over which REPLs are not contributing anything positive to our to the mission or to our users is also good for the business, because it allows us to run more efficiently. And well, that's it. But I would be remiss if I didn't mention that this is actually running on a REPL. These are the addresses, and like this top one is the address in which you can access the presentation. This is the address of the REPL itself if you want to fork it and modify it. We have a blog where we post all of the interesting things that we do engineering-wise and also product-wise and whatever. And finally, we are hiring. We're a remote-first company, so if you're interested in this, please hit that address. And that is all. We are open for questions and answers. Thank you very much.
Before the questions and answers, congrats. Thanks a lot in the name of Crafthub.
Thank you very much.
And now, guys, you can shoot. OK, first question. Why did you choose Docker instead of Kubernetes?
Why do we choose Docker? So we're currently using Docker instead of more advanced orchestration environment, just because it gives us a little bit more flexibility about the lifetime of the containers. Like I mentioned before, since we want the lifetime of the containers to not be tied to like a specific connection, using raw Docker gave us a lot more flexibility. Also, we use a lot of file system shenanigans. We bind mount and overlay mount and do all sorts of neat tricks with the file system just because we want we want to provide caching for most packages available to our REPLs. The 80,000 packages that I mentioned that we provide for free for every single REPL, that is done through a shared overlay FS mount that is shared across all the containers in the machine. So it was a little bit harder to do that with Kubernetes. Not impossible, but a little bit harder. So we chose to do it by hand just because of that extra flexibility. And also because it was faster to implement at first, and since it's still working, why change it if it's working?
OK, before we got deeper into questions, if you are interested in the raffle, it's at 3:20 on the main stage. So you have 3 or 4 minutes to go to the main stage. But if you want to stay and see the Q&A, you are more than welcome. So next question. If you knew that giving out free REPLs was risky, why did you even push the idea to production?
So the mission is what drives what the company is doing. We knew that this was a risk, but still, giving out free compute is the easiest way in which we can achieve the mission. Having said that, we have a decent control over abusers. So it is an intentional trade-off that we're doing and are still doing. Also, we just hired our first abuse prevention engineer. So they will be helping us combat this even more and more systematically and more automated and more in-depth.
That's cool. OK, malicious code can often be hidden deep down. What if all of the abuse detection stages fail, including the manual intervention? What can happen with Replit?
Good question. We have seen cases in which this has happened. Some folks, like, just by a trial and error, figure out the right limits to, like, CPU limits to run their code so that they evade detection, and it is hard for us to quickly identify it manually, but malicious code still has like footprints and has like signals that are weird compared to all the other code that we run. The overall behaviors are significantly different, just because in the end, what abusers want to do is maximize something, right? So if they want to maximize like the amount of Bitcoin they're mining, they're going to leave the container running for as long as possible with a significantly high CPU rate. If they lower that to a threshold where it's not noticeable, then it's not cost effective for them. So that's mostly how we evade getting into trouble long term. So TLDR, it still kind of works.
That sounds good. Why decided on GCP instead of Azure, AWS or Azure?
Great question. So initially, we did start in AWS, but we eventually chose GCP for several technical and non-technical reasons. The technical reason is that GCP's cloud storage has better semantics about how you interact with objects. With AWS, you can just like put an object and read the object. With GCS, you can tell, please put the object, but only if it hasn't been modified since this point in time. So that extra primitive was very useful, and is still be super useful to do safer concurrent editing of REPLs.
Okay, there was one more question which I would really interested. How do you know that someone is mining Bitcoin or not?
How do we know that somebody's mining Bitcoin? As I mentioned before, the signals are pretty high when people are mining Bitcoin. Unfortunately, I cannot give like the full detailed answer just because that would be a recipe for people to evade the detection. But it is quite noticeable. Like if you explore, if you like plot the signals of somebody that's mining Bitcoin versus somebody that's doing something more normal, it is very different. Like the workload profile is different. The network bandwidth is different. The kind of binaries that are being run are different. So it is, they give themselves away, fortunately for us.
That's okay. So plus for you. Thanks a lot. Now the time.